We will now talk about non-additivity and diagnostic plots. After performing a mean effects only analysis, we can actually see if the residuals show patterns of non-additivity. If that is the case, then we consider transforming our data, and the diagnostic plots can be used for our decision making. So we need to first learn what is a diagnostic plot. See, it is a plot of the residuals against the comparison values, where the residuals are plotted on the y-axis and the comparison values on the x-axis as such, which approximately yields a line with a slope of 1 minus p. So why do we use a diagnostic plot? So our motivation is when we plot the residuals against comparison values, its slope would indicate whether or not a power transformation would promote additivity. Its slope, which is 1 minus p, indicates what pth power transformation would be helpful in removing non-additivity. So when we examine our diagnostic plots, we abide to this criteria. If the plot does not yield a reasonably straight line pattern, then no power transformation is necessary. Why? Because if we cannot discern a straight line from the plot, then it is reasonable to assume that its slope is equal to 0. That is 1 minus p is equal to 0, which means p is equal to 1. So technically, this diagnostic plot is suggesting for a pth transformation of 1, which is just equal to the original dataset. So let us try and plot a diagnostic plot in our example, weight gain in pigs. So let us use our final table for the median polish. So here are our residuals or estimates. Now, our goal is to construct a comparison values table, which is given by this formula. That is, the comparison value in cell RCL is equal to alpha hat sub R times beta hat sub C plus alpha hat sub R times gamma hat sub L plus beta hat sub C times gamma hat sub L over mu hat. So let us try and compute for the comparison value in cell 111. So R is equal to 1, RC is equal to 1, and RL is equal to 1. So given the estimates that we computed earlier, here are the needed values. Our alpha hat sub 1 is equal to negative 19.8310546.875. Our beta hat sub 1 is equal to 0. Our gamma hat sub 1 is equal to negative 20.25. And our mu hat is equal to 250.09912109.375. So we just substitute these values in the equation, and we will get 1.60567880313079. And just apply this to all the cells, and we will end up with a comparison values table that looks like this. Now the next step is to just plot the comparison values against the residuals. So that is 1.605679 is plotted against negative 2.01807. Negative 1.60568 is plotted against 46.4819, and so on and so forth. So our diagnostic plot will have exactly 24 points. If we've done that, then we'll end up with a diagnostic plot that looks like this. Examining further, we can see that there isn't really a straight line formed by the points. So our examination, since there is no discernible straight line formed in the diagnostic plot, this suggests that 1 minus p is equal to 0 or p is equal to 1. We may therefore conclude that there will be no benefit from transforming the data. And that is it for non-additivity in diagnostic plots. This is also the end for the discussion on the analysis of three-way tables. Thank you.